Okay, imagine this for a second. You're in an airplane, flying through thick, soupy clouds, miles above the ground. You can't see a thing. So how in the world does the pilot know how fast they're going, or even how high up they are? Well, it all comes down to this really elegant, deceptively simple system that measures the very air the plane is flying through. Let's get into it.
Right. This is the big question, isn't it? A car can just measure how fast its wheels are turning against the road. But a plane? It's just floating in this massive body of air. The secret isn't about what the plane sees, but what it feels. Specifically, it's all about the pressure of the air rushing past it.
So here's the game plan for this explainer. We're going to break it all down. First, we'll talk about the two key pressures that make flight possible. Then, we'll look at the actual hardware that senses them. We'll also get into how these instruments can sometimes be tricked, cover the amazing safety systems built in, and wrap up with the pilot's absolutely critical job before the plane even moves. All right, first things first. To really get this, you have to understand that for a moving airplane, air pressure isn't just one thing. There are actually two different kinds of pressure, and they are both absolutely vital. So first up, we have what's called static pressure. You can just think of this as the baseline pressure of the air at any altitude. The higher you go, the less air is stacked on top of you, right? So the static pressure goes down. It's kind of like when you dive into a swimming pool. The deeper you go, the more you feel that pressure from the water above you. That's static pressure in a nutshell. The second type is dynamic pressure. Now this one is all about impact. The best way to get a feel for this? Stick your hand out the window of a moving car. That force pushing your hand back? That's dynamic pressure. The faster you go, the harder it pushes. Simple as that. And this little equation right here is the magic trick. There's a special sensor on the plane called a Pitot tube, and it measures the total pressure. And total pressure is just the static pressure and the dynamic pressure added together. So if the plane's computer knows the total pressure and it knows the static pressure, well, it just has to do some simple subtraction to find the dynamic pressure. And that is the secret sauce for figuring out airspeed. Okay, so the physics makes sense. But how does a plane actually measure these invisible forces? Let's take a look at the actual hardware that gets the job done. This is just so cool. What you're looking at is a combined pitot-static head, and it's a brilliant piece of engineering. See that opening right in the front? It points directly into the airflow, so it captures that total pressure we were just talking about. But then look at those tiny little holes on the side. They're set up so the air flows right past them. That means they only measure the ambient static pressure without being affected by the plane's speed. It's so clever. One device, two different crucial measurements. And you can see here why getting these readings right is so important. They feed a whole bunch of instruments in the cockpit. Your altimeter, which tells you how high you are, and your vertical speed indicator, they only need static pressure. But your airspeed indicator and your Mach meter, they need both pitot and static pressure to work. So yeah, if you get one bad reading, it can throw off a whole suite of critical instruments. Now, wouldn't it be great if these measurements were always perfect? Of course. But we don't fly in a perfect world. There are a few things out there in the real world that can actually cause these incredibly sensitive instruments to lie. And this image pretty much says it all. On the left, you see the dream, perfect, smooth airflow. That's what engineers design for. But on the right, well, that's reality. The plane's own body creates all this choppy, turbulent air, and those disturbances can totally mess with the pressure right where the sensors are trying to get a clean reading. This brings us to a problem that engineers call position error, and it's exactly what it sounds like, an error caused simply by where the sensor is located on the plane. You can put it anywhere you want, but the air flowing right next to the plane's body is just different than the undisturbed air a few feet away. It can easily trick the sensor into reading a pressure that's a little bit off. And on top of that, just moving the plane around can cause issues. You know, during a really sharp climb or descent, the instruments can lag for a second. They just need a moment to catch up to what the plane is actually doing. It's usually a short-term thing, but hey, when you're flying, every second can count. So knowing about all these potential glitches, you're probably wondering, how do engineers make sure this system is reliable? Well, that's the beautiful part. They design for failure. They build in layers and layers of backups and clever solutions. And here are just a few of those solutions. To stop ice from clogging the tubes way up at 30,000 feet, they have little electric heaters inside them. To get rid of any rain or moisture that gets in, tiny drain holes. And this is really smart. To deal with errors when the plane is turning or slipping, they put static vents on both sides of the plane and then connect them, which basically averages out the readings for a much more accurate number.
But what if the worst happens? What if the main vents get totally blocked by ice or, I don't know, a bird's nest? Well, there's a backup for that too. This is the alternate static system. The pilot can literally flip a switch and the instruments will start pulling air from a different spot, a lot of times from inside the cabin itself. It's not a perfect reading, but it's more than good enough to keep flying safely. And it's a real lifesaver when the main system fails.
All this technology is just incredible, but none of it is completely foolproof. And that brings us to the final and maybe the most important layer of safety, the human in the cockpit. We're talking about the pilot's pre-flight inspection. Because before a plane even thinks about taking off, it faces some surprisingly low-tech threats. Believe it or not, wasps absolutely love to build nests inside these little tubes. Dust, sand, you name it, can clog them up. And honestly, one of the most common problems is that someone just forgets to take the protective covers off after the plane's been parked. And this is exactly why the pre-flight check is an absolute non-negotiable ritual. The pilot has to walk around the aircraft and physically see that all the covers are off. They have to look into every single opening to check for blockages. And they have to test that little pitot heater to make sure it's getting warm. It's a simple routine that stops a disaster before it can even begin.
And while the basic idea here is totally analog, just measuring pressure, in a modern plane, it gets a high-tech upgrade. As this quote explains, that raw pressure data is fed into something called an air data computer. It's a digital brain that takes the readings, corrects for any known errors, and then sends that clean, perfect information to the pilot's displays, the autopilot, and all the other advanced systems.
So, at the end of the day, here's the bottom line. What looks like a really simple system for measuring air pressure is actually this incredibly sophisticated, resilient piece of engineering. Thanks to some very clever design and all those layers of backups, it gives pilots the two most fundamental pieces of information they need, altitude and speed, so they can fly safely even when they're completely blind.